So this is the third lecture out of chapter 6. So in this lecture, we'll cover what's known as the SN1 reaction. And so this is an example of an SN1 reaction. So if we took tert-butyl bromide and reacted it with water, so what happens in this mechanism is the first step is the leaving group leaves. So it just leaves on its own. So the carbon-bromine bond's not that strong, and so the bromine just leaves and it takes the 2 electrons with it. So if you notice the arrow originated from the bond and it ends up on the bromine. So the bromine's taking those 2 electrons and it's leaving. And so that carbon now only has 6 electrons around it. So if you calculate the formal charge, 4 valence minus 3 lines minus 0 dots, it's +1, so that carbon's +1 charged. So that's what's known as a carbocation. So SN1 reactions always make carbocations in their first step. And that's the slowest step in the reaction, so that's what's called the rate determining step. So if you remember the kinetics chapter from General Chemistry 2, so the RDS is the rate determining step. And so what happens in the next step is now the nucleophile reacts. So take a lone pair of electrons on the nucleophile and make a bond to that electron deficient carbon. So now you have a bond from oxygen to carbon and the 2 hydrogens are still there, but now oxygen only has 1 lone pair. And if you calculate the formal charge on oxygen, 6 valence minus 3 lines minus 2 dots, it's +1. So oxygen is now plus and carbon is now neutral. And so that's the second step in the mechanism. And then the third step in the mechanism is you lose a hydrogen. So you lost a bromine in the first step. So you lost a Br- in the first step, and that Br- can remove a hydrogen atom, and the 2 electrons in the OH bond become a lone pair on the oxygen. So losing hydrogen is the third step in the mechanism. So whereas SN2 is a one-step mechanism, everything happens at the same time. In the SN1, it's a multi-step reaction. You lose the leaving group and then the nucleophile attacks, and then if you have a hydrogen on the nucleophile, so if the nucleophile comes in neutral, then it becomes positive in the second step, and so then you have to lose a hydrogen in the third step. And so then you also make an HBr side product. But then the alcohol would be your major organic product in this case. So again, you do a substitution, right? The nucleophile substituted for the leaving group. So that's what the S stands for. And again, it's a nucleophile that does the substituting. And then the 1 means it's a unimolecular reaction. So the rate only depends on one thing. Right, the rate only depends on the alkyl halide that you started with. So the rate only depends on this. And it's because that's the rate determining step, the first step in the reaction, and the only thing participating in that step is the alkyl halide. So the nucleophile is not participating yet, so it's not part of the kinetic equation. So if you double the concentration of water in this reaction, it does nothing to the rate. Right, so it's a unimolecular reaction. It's a first order reaction. The exponent there is 1. So if you take the water concentration and you double it, then the rate is not changed. If you double the concentration of the alkyl halide, then the rate would double. If you tripled the concentration of the alkyl halide, the rate would triple, right? Okay, so that's one of the characteristics of an SN1. Right, that the rate only depends on the concentration of the alkyl halide and not the nucleophile. Also, same with SN2, the leaving group. So iodide bond is the weakest, and then carbon-bromine bond, and then carbon-chlorine bond. So we typically don't see carbon-fluorine bonds used here because the carbon-fluorine bond is very strong. So same is true for SN1 or SN2. And then for the SN2, though, we typically have a weak nucleophile instead of a strong nucleophile, like we did in the SN2. And then it's a multi-step. Can't spell. So it goes through a multi-step mechanism with the carbocation intermediate, right? So what does it mean for that to be an intermediate? So if we looked at the reaction profile, or the reaction coordinate diagram, so you start some energy with your starting material. We have bromide. And then you go through a transition state to make the carbocation. So it's a real species. So in theory, you could isolate the carbocation and stick it in a bottle. Some carbocations are stable enough that you can do that, but most of them are not. Most of them are pretty unstable, and as soon as you make it, it reacts in a subsequent step, which in this one does. So it reacts with the water at this point. So then you would have another intermediate, and then the water loses the hydrogen to make the alcohol as your final product. So it's a three-step mechanism, right? 1, 2, 3 steps. So you go through 3 transition states. So I did not sketch the transition state here. I could have sketched the transition state because all reactions will go through a transition state, right? Where you break that bond and then you make that. So I just didn't sketch a transition state because the mechanism is kind of long enough already, but they're there. So you could have sketched a transition state as here as well, where you make the bond to the oxygen, and then on to the second intermediate, and then we could have sketched the transition state here as well. Where you break an OH bond and make a bond between hydrogen and bromine, and then on to the product. Okay, so what are some other characteristics of an SN2? So let's compare the reaction that we did with the tertiary alkyl halide. Well, what if we had a methyl halide instead? So if it does an SN1, then the bromine would have to leave to make a carbocation. And so the question is, which carbocation is more stable? The tertiary carbocation or the methyl carbocation? And so carbocation stability is just like free radical stability. So we've already talked about free radical stability. So if these were free radicals, which one would be the more stable? It would be the tertiary one. Right, so the point is this carbon does not like being positively charged. So it'll pull electron density of whatever it's attached to. In this case, 3 carbons to help neutralize some of that positive charge. So it will delocalize some of the positive charge to the carbons. And carbons have more electrons. So carbons have more electrons to share. Than hydrogens do. So the carbons attached to methyl can do a better job of stabilizing that positive charge, so that makes the carbocation more stable, so that makes it easier to form. If it's easier to form, then that reaction pathway is going to be faster. So this pathway, so this carbocation is going to form more readily, so that pathway is going to be faster than making this carbocation, that's methyl, and so that's going to affect the overall rate of the reaction. So similar to opposite of SN2 reactions. For SN1 reactions, tertiary reacts the fastest. And then secondary, and then primary, and methyl reacts the slowest. Okay, so let's take some other examples. So it turns out SN1 reactions are more complex than SN2 reactions. So if we do that reaction, for example, so now we have 3 mechanisms that we've learned in this class. We have free radical reactions, where they go through initiation, propagation, termination steps. We have SN2 reactions, and we have SN1 reactions. So 3 mechanisms, and so which one is this? So which does this fit the characteristics of? Well, you know it's not free radical, because the only free radical reactions we've looked at so far in this class is Br2 in lighter heat and Cl2 in lighter heat. And there's no Br2 or Cl2 in lighter heat in this reaction, so it's not a free radical. It's SN1 or SN2. So how do you know which it is? You got to characterize. So this is secondary. SN1 and SN2 are both okay. But your nucleophile is ROH, and that is weak, right? So that's ROH, so that's a weak nucleophile. So that eliminates SN2, and that means this is an SN1, because SN1 likes weak nucleophiles, right? Okay, so if this is going to do an SN1 reaction, then what happens is the bromine leaves in the first step. You would make that carbocation, and then how do you characterize that carbocation? So that would be a secondary carbocation, right? Is that the most stable? No, tertiary is more stable. So carbocations can undergo what's called rearrangement in order to get to a more stable carbocation. So how can they arrange? We'll look at 2 ways that they can rearrange. One is by what's called a 1,2 hydride shift, or they can do a 1,2 methyl, or technically a methide shift. So in this case, what's going to happen is that this hydrogen can move over. And that's what's called a 1,2 hydride shift. Why 1,2? Because with respect to each other, that's carbon 1, that's carbon 2. So with respect to the carbocation, the next position is carbon 2. So it's moving from one carbon, the adjacent carbon, to the carbocation carbon. And so now the structure looks like this. So now the carbocation carbon has 2 hydrogens on it, so it's got an octet again, but now the carbon that had the hydrogen is now electron deficient. So now that carbon is positive, and that is a tertiary carbon. So that's a more stable carbocation. Okay, so what happens now is now the nucleophile reacts. So I'll take a lone pair of electrons on the nucleophile and make a bond to the carbon that's electron deficient. And now the oxygen of the alcohol has a positive charge, and then the last step in the mechanism is to lose a hydrogen. So the 2 electrons in the OH bond become a lone pair of electrons on carbon. And now that oxygen has 2 lone pairs. And you have an H+, just floating around in solution, in the solvent. So it's fine to depict the hydrogen coming off that way, or as we did in the first example, so chemists would always typically depict it like this, just lose an H+ from the molecule, and the H+ then goes floating around in whatever the solvent is. Or it would be fine to depict it like this as well, or the Br- that you lost, or it could be Cl-, or it could be I-, whatever the leaving group was. You could take a lone pair of electrons on it and make a bond to that hydrogen, and then the OH electrons become a lone pair. Let's just do this. So of course you get to the same spot, and then HBr, which ultimately is what's going to happen to the H+. It's going to find the Br- in solution. So the H+ could have come off one of 2 ways though. So it could just come off and go floating around in solution, or the Br- could come in and take the hydrogen off to give you the HBr side product. Either is fine. Okay, so let me just draw this reaction again. So SN2 reactions are a little bit harder to predict than SN1. SN1 reactions are a little bit harder to predict than SN2 reactions, and one reason is because you always have to be conscious of this possibility for rearrangement. Just making sure I got the molecule drawn right. So, you know, if you're not thinking about the rearrangement as well, so you recognize that's going to be the nucleophile, and that's going to replace the bromine. So you might be tempted to just put the nucleophile where the bromine is and do the substitution, and that does happen, but that's a minor product. And if you recognize the carbocation rearrangement, where you go from the secondary carbocation to the tertiary carbocation, then that's the major organic product. And the only way you recognize that product is to recognize the carbocation rearrangement. And so every single time you do an SN2 reaction in this class, you always have to be conscious of a possibility for a rearrangement. And we'll look at a few more examples so that it becomes easier to hopefully identify that. But in general, anytime you make a carbocation, you always have to look for a possibility for rearrangement. So basically they can rearrange by moving a hydrogen from the adjacent carbon over, or you can move a methyl group over as well. It can be more complex than that, but we're going to keep it pretty simple and just look at hydrogens and methyls moving. Okay, so let's see. Go back to our characteristics. So sixth characteristic. Is carbocation rearrangement that you always have to be conscious of. Okay, so we'll stop there. I'll give another lecture over SN1. We'll look at more examples of that. Okay, so that's it for this lecture.